Good day. Today we're going to discuss exponential function. When we say exponential function is actually a function that has a form of f of x is equal to a times b raised to x, where b is greater than 0 and b is not equal to 1. So this function is different from the previous functions since the independent variable is in the exponent. So as we can see here, a and b are both real numbers. However, our x is in the exponent. Therefore, it's quite different from the previous previous functions that we already discussed. Now take note that b should be greater than 0 and b is not equal to 1. Okay, now let's have graph of exponential function. Now let's say that our function is f of x is equal to 2 raised to x. Now observe what will happen to the graph. Now let's try to plot some points in the function 2 raised to x. Now let's say, okay, our x, then we have 2 raised to x. Let's say our x is 3. If x is equal to 3, then our y is equal to 8. If we are going to substitute, because we have 2 times 2 times 2. Now, if we are going to plot that one, okay, we have 3, 8. Okay, so that's the point. Now, let's say we have 2. Our x is equal to 2. And our y is equal to 4. Because the x is replaced by 2. So, therefore, we have 2 raised to 2. That's equal to 4. So, plot, we have 2, 4. Next, if x is equal to 1, y is equal to 2. Okay. If x is equal to 0, our y is equal to 1. Okay. Now, if our x is equal to negative 1, we have to recall that if something like this, if our exponent is equal to negative 1/2, negative 1 rather, then we can rewrite this whole term as 1 over 2 or 1/2. Okay, so that would be our next point. Next, if x is equal to negative 2, then you have 1/4. Okay, it is just the reciprocal of 4. Okay, and then we have that is our next point. And then our last point, if x is equal to 3, negative 3 rather, then we have 1 over 8. Now, if we are going to plot the points, and then we are going to graph. Okay, so that would be the graph. As you can see here, that is the graph of our f of x is equal to 2 raised to x. Now, if that would be the graph, okay, what are the characteristics of the graph of an exponential function? We could say that the domain, okay, for example, the question, what is the domain of the exponential function? So remember that the domain are these values. Okay, so these values are, of course, all real numbers. Therefore, the domain are all real numbers. Now, what is the range of the exponential function? Okay, as we can see here, okay, the range is the positive real numbers. Okay, remember that we have b raised to x and b is greater than 1. So here, okay, going upward. So that is our real numbers. Okay, now what is the x-intercept of these exponential functions? As we can see here, there would be no x-intercept. Okay, in the graph, there's no x-intercept. Okay, if we have b raised to x. Now, what is the y-intercept of this exponential function? Okay, the y-intercept is actually 1, because if we can see here, if our x is equal to 0, then the value would be 1. So that's why the y-intercept is equal to 1. Okay. What are these exponential functions increasing or decreasing? Okay, the graph is always increasing if we have b raised to x, where b is greater than 1. Okay, can you see the horizontal asymptote of these functions? So the x-axis, where y is equal to 0, is the horizontal asymptote for x as x approaches to negative infinity. So that's it. Now, let's have, construct the exponential function f of x is equal to a times b raised to x. Okay, let's have this situation. A bacterial culture contains 5,000 bacteria, and the number of bacteria doubles each day. How many bacteria will be in the culture after a week? Okay, so this would be the table. Okay, as we can see here, the initial bacteria is 5,000. Okay, as they increases, as they goes by, the number of bacteria doubles. Okay, now how many bacteria will be in the culture after a week? Now we are going to construct the exponential functions. The exponential function of this situation. Now, our A is actually, the A here is actually the initial number of bacteria. Okay, so notice in the table, when x is equal to 0, associated with y value is the initial value. Okay, so this is our initial value. Because if this would be 0, this is 1. And this is the 5,000. So A is equal to 5,000. Now, the rate of change, which is our B, doubles. So since it is since at each day the number of bacteria doubles, then our B is 2. Okay, so as we can see, since it doubles every day, then it is growth. Okay, now the x is the number of days where x is equal to 7. Okay, there are 7 days in the week, so x is equal to 7. Okay, so our bacteria, is after 7 days is 640,000. In other words, the function, the function of our situation is f of x is equal to 5,000 times 2 raised to x. Okay, next example. Borium-267 rather has a half-life of 15 seconds. Find the amount that remains from 16 milligram sample of this substance after 2 minutes. Now, so if we are going to understand the situation, every 15 seconds, the quantity of borium-267 is reduced to 1/2. Okay, so in other words, this is not growth, but this is an example of decay. Okay, now, and every 15 seconds, the life of the substance, the quantity of the substance is actually decreased by 1/2. So in other words, our B here is, the B is 1/2. And our A, the initial, find the amount that remains from a 16 milligram sample. So this is our initial. Okay, now, so every 15 seconds, from 16, we have 8, we have 30, and comes 4, and 45, we have 2, and so on. Now, the initial value is 16. Okay. The rate of change is 1/2. Okay. Now, the x is the number of half-life that occurs every 15 seconds. Since in 2 minutes, we have 120 seconds, we have to divide the 120 by 15, and therefore, the number of cycle, okay, or the interval, the number of intervals, okay, is 8. Therefore, our x is 8. So substitute, okay, f of x is equal to 16 times 12 raised to, not 12, times 1/2 raised to 8. Then there would be 0.0625 milligram of barium 267 remains after 2 minutes. Okay. So the function is f of x is equal to 16 times 1/2 raised to x. That's the function. Now, another example. The number of bacteria in a certain culture doubles every half hour. At 10:30 a.m., there were 2,000 bacteria in the culture. Write the exponential function to match this scenario. At what time were there 1,000 bacteria, and how many bacteria will be there at 1:30 p.m. Now take note that in our problem, okay, as we can see, every half hour, the culture would be doubles. And then, before the observation, there are 2,000 bacteria. So in other words, this is our A and this is our B. Okay. So to write an exponential function, the initial amount is 2,000, and then the rate of change doubles every 30 minutes. So in other words, our function is actually f of x is equal to 2,000 times 2 raised to x. Okay, at what time were there 1,000 bacteria? Okay, so reverse the rate of change from 2 to 1/2. The exponent will be 1, and as only 1 30-minute interval will have lapse. So you have 2,000 times 1/2 raised to 1 will equal to 1,000. And 10:30 minus 30 minutes is equal to 10 a.m. Okay, how many bacteria will be there at 1:30 p.m.? Now, using the equation from part A, f of x is equal to 2,000 times 2 raised to x, calculate the number of times the bacteria will double from 10:30 to 1:30. Okay, so there would be 3 times 60. Okay, since there are 3 hours from 1:30, from 10:30 to 1:30, so there are 3 hours. So 3 times 60 is equal to 180 minutes. And then, because the bacteria doubles every 30 minutes, then we have 180 minutes divided by 30. So it's equal to 6 periods. So 6 times the bacteria will double. Okay, so substitute. So f of x is equal to 2,000 times 2 raised to 6. So there would be 128,000 bacteria in 1:30 p.m. Okay, another example. Okay, this would be our last example. Cesium-137 is a radioactive element with a half-life of 30 years. How much of a 50 milligram sample of cesium-137 would remain after 180 years? Write the exponential function to match this scenario, and how much cesium-137 will be there in 180 years. Now, remember that, okay, we have the initial amount is 50. And then the half-life, the one half, would be every 30 years. So our equation would be 50, f of x is equal to 50, the initial, times 1/2 raised to x. Okay, so that would be our exponential function. Now, using the equation, okay, calculate the number of times the element will occur a half-life rather. Now, in 180 years, okay, we have to divide it by 30. So in other words, there are 6 times the element goes to half-life in 180 years. So in other words, we are going to substitute. This would be our x. So our f of x is equal to 50 times 1/2 raised to 6, which is equal to 0.78125 milligram of cesium-137 will remain after 180 years. And that's all for this topic.